Okay, so in this video, we're going to start talking about wave interference. We're still in 4.4, which is called wave behaviors. And so remember, everything under 4.4, all of those behaviors can apply to any type of wave: transverse wave, longitudinal wave, mechanical wave, electromagnetic wave. And so interference is something we've kind of briefly mentioned before, but today we're going to go into more detail about it. And basically the concept of interference kind of arises because of what's called the principle of wave superposition. And you should remember from the last unit we did that wave superposition basically talks about what happens when two waves occupy the same point in space. What happens when two waves run into each other. And basically, superposition says that when two or more waves meet, their displacements combine together algebraically as they pass through the same location in space. Okay, now how does that pertain to interference? Well, if you reach a point where you have two waves meeting up because of superposition, if you end up with a resultant wave that has an amplitude greater than that of the two individual waves, we call that constructive interference. Okay, think like construction, you're building something up, you got two waves meeting, you're forming a bigger wave. If the resulting amplitude is less than that of the individual waves, we call that destructive interference. Okay, now for some reason that I don't understand, it's very common to mistake this as deconstructive. I guess some people in their mind think like, oh, okay, you have constructive, and the opposite of that would be deconstructive. Deconstructive is not a thing. Okay, you have constructive interference and destructive interference. For destructive, think like destroy. You've got two waves meeting up, and they're kind of canceling each other out and forming a smaller wave, and that is destructive interference. Okay, so just to kind of show you what this looks like, here we have two types of interference happening. On the left side, you can see two wave pulses going towards each other, and as they begin to approach each other and occupy the same point in space, at some moment in time, say right here, they occupy the same point in space, and then they pass through each other and they keep moving. Now, what type of interference is this? Well, you have two wave pulses, each with a positive a positive displacement. When they meet up, notice that they form a resultant wave that is bigger than either of the two wave pulses individually. So this is a classic example of constructive interference. Whereas destructive interference, here on the right side, notice you have a wave pulse with a positive displacement going towards the right, and a wave pulse with a negative displacement going towards the left, and when those occupy the same point in space, for a split second, right here, when they occupy the same point in space, notice that they kind of cancel each other out. Because basically, because of superposition, you're adding a positive displacement to a negative displacement, and if they have the same amplitude, then those two things cancel out. And so this is a classic example of destructive interference, not deconstructive, destructive interference. Okay, and again, going back to the definition, we're forming a resultant wave that has a smaller amplitude than either of the two individual waves. Okay, so put another way, basically you have constructive interference when you have two wave pulses with the same sign displacement meeting up, and destructive interference you have when you have, let's say a positive displacement and a negative displacement meeting up. All right, so pause there if you need to add that to your notes. Just to look at a few more examples. Let's say you have these two wave pulses approaching each other, and it says what is the resulting amplitude when these two waves meet. And by meet, let's just say, just for the sake of argument, because otherwise it gets difficult to think about, but let's say when these two wave pulses completely overlap, what does that look like? Okay, right here on the left side. Well, we know because of superposition that their displacements are going to add together. And so when these two waves are on top of each other, we have a displacement of 1 plus a displacement of 2. That's going to give us a resultant displacement of 3 because of superposition. And that is going to be an example of constructive interference. And I could look at the other ones also, but I think you probably get the point. And so this is kind of what all of these situations would look like when you apply superposition, and these are all examples of constructive interference. Okay, and then on the next slide you can see kind of examples of destructive interference. Notice again that you get destructive interference when you have a positive and a negative wave pulse, or a negative and a positive wave pulse meeting up, because there's some partial cancellation. It doesn't have to be complete cancellation, but you get some partial cancellation. Okay, so let's say in the image on the top left, when these two wave pulses overlap, you have a displacement of positive 2 plus a displacement of negative 1. That gives you a resultant wave with an amplitude of 1. Like you can see here. And so these are all examples of destructive interference. The resultant wave has an amplitude less than the individual waves do. And just one more example of constructive versus destructive interference. Now, if you look at this image, by the way, you can kind of see that you kind of get constructive interference when the two waves that meet up are kind of meeting like crest to crest and trough to trough. In other words, when they're in phase with each other, right? Whereas if you look over here, you can see you get destructive interference, at least maximum destructive interference, when the two waves are out of phase with each other. Specifically, if you look on the right side here, this is a phase difference of basically pi radians, or 180 degrees, or half a period, if you will. Okay, and so when that happens, notice you get destructive interference. So you can also think of constructive and destructive interference in terms of, what is the phase difference between those two things. And again, if the two waves are completely overlapping, like you see here on the left, the phase difference is 0, or 2 pi radians, you get constructive interference. And over here you get destructive interference when they're half a cycle out of sync, with a phase difference of just pi radians. Now, before we get too much into talking about phase difference and what mathematically causes interference, I want you to see some of these videos having to do with applications of interference. These are partially to help you understand the concept of interference, see what it looks like in real life. Pay special attention to the last video. That's called the original double slit experiment. We are going to be talking about the double slit experiment in the next video after this one, and that is something that you're responsible for knowing about for the IB curriculum. And so this is just going to kind of guide you into that type of thinking. Okay, so check out those videos about applications of interference. Okay, and just one more quick application, noise canceling headphones. Basically, the way those work is there's like a little microphone in the headphones, and when there's like external sound out there, the sound goes into the microphone that's in the headset, and basically it generates a new noise that is 180 degrees out of phase with the outside noise, and basically by combining those two sound waves, you get some cancellation, you get some destructive interference. And so that's how noise canceling headphones work. Okay, and so there's circuitry and like I said, a speaker and a microphone inside your headset that allows that to happen pretty quickly, depending on how what is the quality of the headphones. Usually you have to pay more for good quality noise canceling headphones, because it's not that easy to achieve. But that's how that works. That takes advantage of destructive interference. Alright, so make sure you take really good notes on this slide as we talk more about interference. Okay, so add this to your notes. Okay, so we've talked a little bit about interference before. I mentioned previously that interference can happen whenever two or more waves meet and have a phase difference of pi radians, or 180 degrees. Here, if you look at this Desmos simulation, you can kind of see the blue line here is basically the superposition of the two orange waves. And so here you can see a phase difference of about 180 degrees. And then if I adjust that slightly so that they're in phase with each other, now there's a phase difference of more like 0 degrees. And you can see we get constructive interference. And so whether you get constructive interference or destructive interference like this just depends on the relative phase shift between the waves that you're talking about. Okay, now in terms of how that happens, okay, let's say you're talking about two wave sources interfering with each other. There's two classic ways that could happen. either the two wave sources are out of phase with each other, and just to make this a concrete example, let's say you've got two speakers each playing the same sound, but one of them is 180 degrees out of phase. If that happens, that could create destructive interference, because then you have like a compression meeting a rarefaction, and you get cancellation, you get destructive interference. Now, you're probably not going to see problems like that on the IB exam, although you could, which is why I'm mentioning that you get destructive interference with a phase difference of pi radians. Typically what you see on the IB exam is that the two sources are actually in phase with each other. It's just that one of the waves travels a further distance than the other. Okay, and so there's what's called a path difference between the two wave sources. When I say path difference, I literally mean the difference between the distance that one wave travels and the distance that another wave travels. Okay, so for simplicity, we're going to only look at problems where we have what's called interference of coherent waves, meaning that the two waves have the same frequency and are in phase with each other. And so we're mainly only going to focus on interference caused by path difference, although technically speaking, you could also have the two sources out of phase with each other. And again, I mentioned that not because it's super common to see on the IB exam, but it is something that might pop up. Okay, so what does this mean, path difference? Okay, so here is an example, and this kind of goes back to the double slit experiment. But if you take a look at this, let's say S1 and S2 are two sources of a wave. You can think of the double slit experiment like, two sources of light, or you can think of two speakers each playing the same sound wave. Okay, so let's say we have two speakers both emitting coherent sound waves. Now, when these two waves meet at some points, along the screen over here, if you look at how the picture is drawn, notice that the wave coming from S2 has traveled a farther distance than the wave coming from S1. Now, why has it traveled a farther distance? I mean, S2 is physically farther than S1 from this point on the screen. Okay, and so that's why the distances are different. Now, notice that S1 and S2 are in phase, meaning that if you look, S1 starts at 0 and the wave goes down, S2 starts at 0 and the wave goes down, and they are in phase with each other, but there's what's called a path difference between the two. And so when I say path difference, I mean the difference, meaning you're subtracting the distance that the wave coming from S2 travels minus the distance that the wave coming from S1 travels. In other words, if you were to make a cut right here, these two waves are exactly the same length, and the difference between the two paths, in other words, the extra bit that S2 has, is right here. And I'm putting a box around. And so this is what we call PD, which is called the path difference. Now notice that this path difference is a length, by the way, because it's the difference between two distances. Notice that in this case, the path difference is actually one wavelength. Notice that we have one full back and forth that I put a box around. So here I would say that the path difference between S1 and S2 is one wavelength. Now, what ends up happening? Well, if you look at the very end, despite there being a path difference, notice that you still end up with a crest meeting a crest at point R on the screen. And so we are going to get constructive interference over here at point R. Okay, so in other words, I'm telling you that there's a relationship between the path difference being one wavelength and there being constructive interference at point R. And that's what we're about to see in more detail. Okay, the path difference and how it relates to the wavelength is ultimately what's responsible for types of interference, assuming that the two wave sources are in sync and they're not out of phase. Okay, so pause it here and understand exactly what path difference is. It is the difference between two distances, the distance that a wave coming from one source travels versus the wave coming from another source. Okay, that's why path difference is measured in units of length. Alright, so just to make this more concrete, let's take a look at some examples. Okay, so take a look at A right here. We've got two waves meeting up. and their superposition and whatnot. Think about what's going to happen when these two waves meet. Well, you're going to get destructive interference. We should know this at this point. This is going to produce destructive interference. This over here is also going to produce destructive interference. D is going to be constructive interference, and B is also going to be constructive interference. Okay, you should be able to tell just by looking. But notice now that this picture kind of highlights the path difference between the two waves. Okay, notice that these two waves, if you stop at the dotted line, are the exact same length, but the bottom wave here is a little bit longer. The extra bit, that is the bit between the two dotted lines, this is what we call the path difference. So here's the path difference here, here's the path difference here, here, and here. So let's see if we can make a connection between path difference and what type of interference we get. Notice that for A, the path difference here, in terms of the wavelength, is half the wavelength. Okay, because we have the down part of the wave, but we don't have the up part. So what I would say here is the path difference is equal to lambda over 2, half the wavelength. Here, the path difference, let's see, we have one down and up, and then we have another down. Okay, so here I would say that the path difference is equal to 1.5 wavelengths, which I can write as 3 lambda over 2. Okay, so I want you to start to see the pattern between when we get destructive interference. Just to give you a hint, if we had a path difference of 5 lambda over 2, that would also cause destructive interference. Whereas constructive interference, if you look, here the path difference is 1 wavelength. What is the path difference here? Okay, well, this is 2 wavelengths. We have one back and forth, and then another back and forth. And so this path difference is 2 lambda, 2 wavelengths. Okay, so notice we have 1 lambda here, 2 lambda here. If we had 3 lambda path difference, that would also be constructive interference. Okay, and so hopefully you're starting to see the pattern here between path difference in terms of wavelength and what type of interference that produces. Okay, so pause there and make sure you understand what I'm talking about. Alright, so make sure you add this to your notes. Constructive interference, just to summarize like what you were supposed to see on the last few slides. Basically, you get constructive interference when the path difference is an integer, I should say a positive integer, number times the wavelength. In other words, the path difference, you get constructive interference as long as the path difference is equal to n times lambda, where n is equal to 1, 2, 3, 4, and so on. Destructive interference, on the other hand, destructive interference, you get when the path difference is, I call it a half integer multiple of the wavelength. In other words, when you have n plus 1/2 times lambda, where n is equal to 0, 1, 2, 3, 4, and so on. I guess you could also have 0 up here as well. Okay, so make sure you write that down, although I will tell you that this is actually the data booklet, more or less. Okay, so this is what's given to you in the data booklet for 4.4. We have Snell's law, kind of like in a weird rearranged way. This middle equation right here is called the double slit equation. We'll see that in the next video. And then down here at the bottom, this is what's given to you in the IB data booklet, the conditions for constructive and destructive interference in terms of the path difference. Okay, just to show you some more examples, here we have basically the situation we had before, where we have S1 and S2. You can see that the red wave is longer than the blue wave, and the path difference here is 1 wavelength. Because here this length is 7.5 wavelengths, this is 6.5 wavelengths, so that's a path difference of 1 lambda. And so you get constructive interference here, like you can see. Notice, by the way, if you think in terms of the double slit experiment with the two slits, notice that what type of interference you get changes depending on where you fall along the screen. So here in the middle, you have a path difference of 0, because right here in the middle of the screen, the distances from each slit are the same. So this would be a point of constructive interference. Whereas if you move along the screen, you can actually arrange it so that you get a path difference of half a wavelength. And if you keep going, then basically what you see on the screen is you get alternating patterns of constructive interference and destructive interference. Constructive interference and destructive interference. And so it alternates back and forth. Okay, and just to show you some examples of what that looks like, take a look at this. Okay, so this is basically the double slit situation right here. And you can see the alternating, spots of constructive interference is where, you have a bright spot, and then you have a black spot where it's destructive interference. And again, it alternates back and forth because as you go along the screen, the distance becomes such that you get places where sometimes the path difference is an integer multiple of the wavelength, and sometimes it's a half integer multiple of the wavelength. This image was in y'all's video, the original double slit video with the two balls. Notice that here you can actually see the lines where there's destructive interference, like right kind of in here you can see where there's basically nothing happening and the water looks calm in that place. And so every place along this line you have destructive interference. Here the water wave is moving the most, and so here you would have constructive interference. And then you have destructive interference, constructive interference, destructive interference, and you can see even with the ripples on a pond it alternates back and forth. Okay, so just a few more examples just to see what this looks like. Two coherent point sources, S1 and S2, emit spherical waves. Which of the following best describes the intensity of the waves at P and Q? Keeping in mind what you're looking at here is the wavefronts of S1 and S2. So see if you can answer this question. Okay, so if you look at point P, notice that you see two lines intersecting, but the two lines are the wavefronts of these two waves. And wavefronts appear at the crests. Alright, so basically if you have two lines meeting up, basically you have a crest meeting a crest, that's going to give you constructive interference, and so you're going to have a maximum intensity at point P. Whereas point Q, you have a line meeting, well, basically a blank space, which represents a trough because wavefronts show you where crests are, and troughs are halfway in between crests and troughs. And so you would have destructive interference at Q, and so the intensity would be at a minimum at Q. And this is the type of question that shows up sometimes on the IB exam. Okay, so I want to do, actually I will come back to example 1, we can do that in class, but I want to take a look at example 2 really quickly, and then we'll end this video. Let's say we have two speakers separated by a distance of 5 meters. They emit a coherent sound signal of 850 hertz. If the speed of sound is 340 meters per second, is this person at a maximum or minimum location? So basically, the question is asking, do we have constructive or destructive interference where the person is standing? Okay, so think of, this is S1 and this is S2. S1 is a distance of 2.1 meters from the listener. S2 is a distance of 2.9 meters from the listener. So what is the path difference? Remember, that is the difference, the physical distance difference between the two wave sources. The wave coming from S2 travels 2.9 meters. The wave coming from S1 travels 2.1 meters. Okay, so that would be a path difference of 0.8 meters. Now, by itself, that tells us absolutely nothing. Okay, we need to look at this in terms of the wavelength. Notice that we have frequency, we have wave speed, and so we can just use the wave equation to get the wavelength. Alright, and so I'm going to go to my calculator and I'm going to type this in. Okay, so when I do that, I get 0.4 meters is the wavelength. Okay, now to assess what type of interference this is, we need to think of the path difference in terms of the wavelength. Well, we can kind of tell what it's going to be visually, but what I would do at this point is I would basically take the path difference and divide it by the wavelength. And if the answer is an integer, then it's going to be constructive interference. If it's a half integer, like 1.5 or 2.5 or 3.5, then it's going to be destructive interference. In this case, we get 0.8 divided by 0.4, which is 2. In other words, the path difference is equal to 2 wavelengths. And so this is going to be a maximum location where we get constructive interference. Alright, so I'm going to leave you just with one example to try to do on your own. Pause it there if you need to finish writing that down. This slide right here basically also has the answer. Okay, so I want you to try to do example 3 on your own. Okay, again, start by finding the path difference, and then finding the path difference in terms of the wavelength, and see if you can answer example 3 on your own. Okay, so I know there was a lot in that video. Hopefully you took really good notes. In the next video, we'll look at a little bit more having to do with interference, and then we will move on to the last part of 4.4, which has to do with diffraction and the double slit experiment. As always, please let me know if you have any questions, and I'll see you guys in the next video.